So we end up with a spectrum that's still periodic with period 2 pi, but in the range minus pi to pi, what used to have this nice triangular shape is now lost due to detrimental aliasing. So we've lost information that was sitting in these frequencies. So now we can even use this idea to restate the sampling theorem. Sampling theorem says that we can reconstruct just going to boost this up a little higher. It's closer to the camera. Sampling theorem says that we can reconstruct the analog signal XA of t from samples x of n, but we can use sort of this idea of a band-limited signal. So if XA of t is sufficiently band-limited, then what I could do is I could take the inverse Fourier transform of t times the discrete time Fourier transform of the samples x of n, so if I have x of n, which are samples of xa of t, then one way I can reconstruct xa of t from x of n is to take the discrete time Fourier transform to get the x of d of omega. If I sampled at or above the Nyquist rate, then scaling by t, and then taking the inverse Fourier transform, appropriately scaling the frequency axis of the dt of t, will give me back xa of t. I'll have to put this kind of in quotes because it's not exactly correct, because I have to rescale this frequency variable. But let's work that out. Let's work out that algebra. So I guess I can make this exact if I say take the dt of t and evaluate that at omega equals omega t. Now it'll be mathematically correct. So let's work that out. So xa of t is the inverse Fourier transform. So let's write down the inverse continuous time Fourier transform. 1 over 2 pi, the integral from minus infinity to infinity of something. What's the something? The something is t times the dt of t of x of n. dt of t of x of n is the sum from minus infinity to infinity of x of n e to the minus j omega n. I'm going to evaluate that at omega equals omega t. That's this rescaling of the continuous time and discrete time frequency variables. Going back to taking the continuous time inverse Fourier transform, e to the j omega t d omega. Okay. So let's just interchange the order of summation and integration. That's the sum from minus infinity to infinity of t over 2 pi of the integral from minus infinity to infinity of what? Well, I've got x of n here. X of n doesn't depend on this integral d omega, so I'm going to bring x of n out here. Actually, I'll just make it simple so I don't have to crowd the space. I'll put x of n outside the integral. My integral is d omega, and it's e to the minus j omega n, where omega equals capital omega t. So I've got e to the j omega t minus n capital T, because I have e to the j omega t, e to the minus j omega tn, e to the minus j omega tn d omega. Okay, now, we said that the DTFT contains all the useful information in the range minus pi to pi. So when little omega goes from minus pi to pi, capital omega goes from minus pi over t to pi over t. So I'm only going to take this integral in that range, minus pi over t to pi over t. Now all I have to do is integrate e to the x. So that's the sum from minus infinity to infinity of e to the j omega t minus nt evaluated. So I just have to take 1 over j t minus nt, j t minus nt. This 2 pi over t sitting out front, or t over 2 pi sitting out front, I'm going to write it down here as 2 pi over t sitting down bottom. Now I just have to evaluate this at the numerator, or at the limits. I have e to the j pi over t, t minus nt, minus e to the minus j pi over t, t minus nt. And you'll recognize this as 2j sine, and this is 2j times this term. So this all can be expressed as xa of t is the sum from minus infinity to infinity of, there's an x of n now down here, dropping down, x of n, sinc pi over t, t minus nt. And that was our band-limited reconstruction formula. We call it a band-limited reconstruction formula because it allows us to reconstruct band-limited signals x of t from their equally spaced samples exactly using this sinc kernel. Okay. Let's look at a couple of examples. Let's start with a real simple ideal low-pass filter, xa of omega, that is band-limited to, let's say, 3,000 pi. What is that in hertz? Well, remember that omega equals 2 pi f. So I've got 3,000 pi equals 2 pi f. 1,500. So it's 1.5 kilohertz.